Hi everyone, this is Dr. Wright again. So in class, we've been learning about summary statistics when it comes to asset returns. We've been talking about arithmetic average returns, geometric average returns, continuously compounded returns. We've been learning about variance, standard deviation, skewness, and kurtosis. So I just wanted to very quickly help us apply some of those concepts. And what I want to do is I want to give it some real-world context. And in order to give it real-world context, I want us to investigate the Standard & Poor's 500. And so I'm just going to pull up some data on the S&P 500, and how we're going to start is we're just going to download historical monthly data going back to 1950 all the way through August 27th of 2012, which will technically only take us up to August 1st. So we're going to download the monthly data for the S&P 500. It's very simple here. I'm in Finance Yahoo. Down at the bottom, I'm just downloading it to a spreadsheet. And I'm going to open up this Excel document. And so you can see here is some data regarding the S&P 500 going all the way back to January 3rd of 1950 and ending August 1st of 2012. First thing I'm going to do is I'm going to resort the data using the date going from oldest to newest. So I just highlight all the data and I sort it. I just hit Alt-DS in case you're wondering what the hotkeys are, but you can also do it with point and click as well, just as easily. So I'm going to sort based on the date from oldest to newest, resort it that way. And actually I don't need any of this data right there, so I'm just going to hide it. And we're going to have our adjusted close, and we're going to focus on that. I'm going to calculate returns. Just as a brief reminder, I want to point out, as we studied in class, that if you remember from your time value of money lectures that you've heard in different classes, that when you have continuously compounded returns, that the way to figure out the future value is to take the present value multiplied by E raised to the Rn, where R is your continuously compounded periodic return and N is the number of periods. So that's how you would calculate the future value if you had the present value and you knew the continuously compounded return and however many periods we're compounding that return over. Well, we don't have that in this case. What we actually have is we have future and present values, and what we want to figure out is the return. So you can do some relatively simple math and figure out that to infer the return based on this relationship, that the return is just the natural log of the ratio of the future value over the present value divided by the number of periods. So that's one way that you can calculate the average continuously compounded return, and we could apply that formula very easily in this situation. But remember, we also learned that there's another way to do that. You can get this exact same result, which again is the average continuously compounded return. The other way to get that is to calculate the continuously compounded return each period. So just every period take the log of the current price over the previous price. And then all you have to do is take the average of those individual continuously compounded returns, and that will give you the exact same result as what we did here. So we're going to apply this methodology. We're going to take the natural log of the current price over the previous price for every period. So all that amounts to is right here in February of 1950, we would just take the natural log of this price, or this level for the S&P 500, over the previous price or level, and that right there represents the continuously compounded return for that 1 month, and we'll turn it into a percent and give it maybe 3 decimal places since we're dealing with monthly returns, and you can send that all the way down. And then in order to figure out the average continuously compounded return, and so maybe up here we'll just put summary statistics, and the first thing that we want is just the average or the mean return, and so we'll just call it the mean, and all we have to do is take the average of all of these individual continuously compounded returns like so, and you can see that the average continuously compounded return since 1950 has been 0.588% or 58.8 basis points. Now the other way that we could have gotten that would have been this. We could have taken the natural log of the ending value over the beginning value. So we're just taking the natural log of that ratio, and then we would have to divide it by however many compounding periods there are. So you could divide that by, again, how many compounding periods are there? Well, just highlight all of the returns. That tells you how many compounding periods there are, and you would get the exact same result. So you can see that's just two ways to get the exact same result. So you might be saying, well, Dr. Wright, you're advocating using this methodology right here. Calculate the continuously compounded return every month and then average it up. Why don't we just use this? You showed us that it gives us the exact same result. Well, I think as we go through the rest of the summary statistics, you'll be able to see why we favor this methodology over here. So I'm going to go ahead and get rid of this since it gave us the same outcome. Let's calculate the median. And so I'm just going to highlight all of these returns using the median function. And we can see the median is 0.906, and so the average continuously compounded monthly return is actually less than the median continuously compounded return. That right there is our first indication that we don't have a normal distribution. And that turns out to be very important when we're trying to make inferences based on summary statistics. So keep that in mind. We have a mean that's less than the median, which means we probably have some negative skewness going on. Let's calculate the standard deviation. And you just have to use the standard dev formulation. And you can see you could do the standard deviation of a population. We'll just do the regular standard deviation formula. And the nice thing about standard deviation is that it's the units are the same as the average and the median. So we can turn it into the same unit. So there's our standard deviation. Why don't we also calculate the higher moments of the distribution? Let's calculate the skewness and the kurtosis. Remember, skewness measures how extreme the values can get, and kurtosis represents the frequency of tail events. So skewness represents how does this distribution lean one way or the other. In other words, do we get extreme outliers on one end or the other? Kurtosis just measures how fat are those tails, so how frequently do we get tail events. So let's go ahead and use the skew function. Okay, now remember, a normal distribution has a skewness of 0. We're seeing skewness of negative 0.665 or 655. Just as we thought we see some negative skewness, we knew we would see that because the median was higher than the mean. So there must be some extreme outliers on the negative end, pulling our average down. Let's calculate kurtosis. It's just K-U-R-T. Again, remember the kurtosis of a normal distribution is 0. So if the kurtosis of a normal distribution of 0 is 0, we have 2.401. That tells us we have fat tails. If we have fat tails, what that means is the actual frequency of a tail event with the S&P 500 is higher than for a normal distribution. So we're going to go ahead and make some inferences based on what we see here, assuming it's a normal distribution, but we're going to have to also note some caveats. And so we'll do that as we go throughout. But the first thing I want to do is I actually want to transform some of this data into annual data, specifically the mean and the standard deviation. So let's annualize this very quickly, and maybe I want to do this. We'll just do this. Annualized. And remember, the way that you annualize the average, if you're talking about a normal distribution, the way that you annualize the average is you just take your average return and multiply it by the frequency of your data. In our case, it's 12 because it's monthly. So we just take the average return and multiply it by 12. Simple enough. Just take the average and multiply it by 12 and apply the same formatting. I'm not going to worry about the median. Let's annualize the standard deviation, however. And in order to annualize your standard deviation, you must take the standard deviation of your monthly returns times the square root of 12. The reason you have to do that is because in order to annualize the variance of your monthly returns, you would multiply the variance by 12. Well, remember, the standard deviation is the square root of the variance. So in order to get the standard deviation of this, you would take the square root, which would be the standard deviation times the square root of 12. So let's do that. Let's take the standard deviation times the square root of 12. And again, apply the same formatting. And we'll just black out some of these cells that we don't need. And forgive me as I just apply a little bit of formatting here to clean it up just a bit for us. Just centering that across the selection there. Centering this to make it a little crisper for us. And maybe we'll do this again just to make it a little bit more readable. And okay, so we have our mean return. Mean monthly return is 0.588%, 58 basis points. Again, that's continuously compounded. We have a median of 0.906% or 90.6 basis points. Because the mean was less than the median, we knew we would see negative skewness. We have a monthly standard deviation of 4.229%. We see the negative skewness manifesting itself when we actually calculate the skewness. And we also see a kurtosis that's relatively high. Remember, a normal distribution, we have a kurtosis of 0, so we see fat tails. Let's try to take this data now and make some inferences from it. So the first thing that I want to do is I just want to come up with the 68, 95, 68, 95, 99 ranges. Remember, according to the 68, 95, 99 rule, we can use the mean and the standard deviation to come up with some expectations about where observations will fall. And so let's do this. We're going to have a lower bound and an upper bound. And this will be our 68% bound, our 95% bound, and our 99% bound. Remember, if you have a normal distribution, which we do not, and we will come up with some caveats here in just a second, but let's assume for now that we have a normal distribution. If you have a normal distribution, 68% of the observations should fall within one standard deviation of the mean. Let's use annual returns. And so what I'm going to do is I'm going to take this average and I'm going to subtract one standard deviation, and that will be our lower bound for the 68% range. Now let's take our average and add one standard deviation. That will represent our upper bound. So we anticipate that 68% of the observations, generally speaking, should fall between that range. So 68% of the time, the return to the S&P 500 in a given 12-month period should be between negative 7.6% and 21.7%. Now the 95% range is defined by two standard deviations on either side of the mean. So we begin with the mean and we subtract two standard deviations. Don't worry, we'll format that in just a second. To get the upper bound, we take the average and add two standard deviations. There we have it. Let's apply our formatting like we talked about. And so we think that 95% of any 12-month periods that we observe with the S&P 500 should fall within the range of negative 22.245% and positive 36.58 or 358%. For the 99% range, we are now going on three standard deviations on either side of the mean. So we start with the mean and we subtract three standard deviations. And now we're going to go on the other side, three standard deviations. So we start with the mean and we add three standard deviations. Again, we just need to give it a little bit of formatting TLC there. And we'll narrow that back down. Okay. And again, forgive me and excuse me here as I just format a little bit just to make it a little bit more readable. Okay, so we've calculated the summary statistics. We've got our mean, our standard deviation. We've also got our skewness and our kurtosis. We made this what we know to be not a great assumption. We assume that it's a normal distribution. If that's the case, we came up with our 68, 95, and 99% ranges. So if this were a normal distribution, we would anticipate that 99% of the time, if we look at any 12-month period, the total return, I should say continuously compounded return for any 12-month period, should fall between 36.896 or negative 36.896 and positive 51.008%. What I would like us to do from this point forward is to just try to test that a little bit or validate that. Let's begin by making some caveats. So what would be the first caveat that I would make? I would say, well, it's got fat tails. What does that mean? Fat tails means there should be a higher probability of tail events. What do I mean by that? Well, we think that 99% of the time annual returns are going to be in this range right here. The fact that there are higher tails or fat tails tells us that we're probably actually going to get a few more outliers than we anticipate. So slightly more than 1% of the time, we're probably going to see observations falling outside of that range. It's also negatively skewed. What does that mean? That means that we have a higher probability of extreme observations in the left tail. What does that mean? Well, putting these two things together, we know it's got fat tails, but it's also got a negative skewness. So we anticipate that we'll see slightly more than 1% outside of this range. Slightly more than 5% outside of this range. The negative skewness tells us that in all likelihood, we'll probably see most of those tail events on the left-hand side. In other words, we'll probably see more observations below the lower bound than we will see observations above the upper bound. So those are the caveats that we just want to keep in mind as we're going through this. Again, forgive me as I just do some formatting here to make it a little bit more readable for us. And I might even highlight these things right here just so we can keep those in mind as we move forward. Okay, so now what I want to do is just want to try to validate this. But in order to validate, what we have to do is we have to actually create some annual returns. And to create the annual returns, I just want to talk for a second about how we can work backwards with this data. So let me just add some columns and show you some things. If you just had this starting value and the returns, how could you recreate the adjusted close? This matters because what if you're saying, well, I have $10,000, I know what my anticipated returns are. How do I then estimate what my dollar value is going to be in my portfolio? So let me show you how you could go from just the beginning adjusted close and your return vector to try to figure out the adjusted close. The simplest way to do it would just be this. You would just take the previous adjusted close and multiply it by E raised to whatever the return is. That's the easiest way to do it. And you could shoot that all the way down the line. And you could see indeed that there's no error there. We're getting exactly the adjusted close. There's actually a second way that you can do this, turns out, and it actually has its roots back here. It has its roots in this formula right here. The fact that we can take the continuously compounded return each period and then just average that tells us that if we go the other direction, instead of averaging it, we can just multiply it to move it forward. So another way to get the adjusted close is to do this. You can say, well, just give me the beginning value and lock that in. So we're just going to always go back to that value and multiply it by E raised to the sum of all of these returns. In the first period, we only have one return. But as we move forward, what I'm going to do is I'm going to lock this in, and you'll see what happens. So there's the formula. We're going to have our beginning adjusted close multiplied by E raised to the sum of all the returns. As I drag it down, watch what happens. Now I have the beginning adjusted close multiplied by E raised to the sum of these two returns right here. And we get the same outcome. If I drag it down one more, now we have E raised to the sum of H3 through H5. So all we're doing is in the exponent, we're adding up all these continuously compounded returns, and you can see we get the exact same result. Well, I'm showing that because I want you to understand, just like we did over here, that once you've figured out a monthly continuously compounded return, the way to annualize it is to just multiply it by 12. Well, okay, that's assuming that you have the same continuously compounded return in every period. So the other way to think about it is over here when you're annualizing your average, it's as if you have the same monthly return, and so you just multiply it by 12. But instead of multiplying by 12, you could just add up those 12 months. So the way to annualize these returns over here is not multiply by 12, it's just add up the last 12 months. So okay, you can see we would get our first annual return right here. Okay, so let's do that. Let's annualize the returns by just adding up the last 12 months worth of returns. Again, that's by the same logic that we used over here. If we could just take this average and multiply it by 12, then we can just add up the last 12 months to annualize. If that's not enough, I proved it to you right here that it works. You can just sum up the last 12 months in the exponent and it gets you the same result. We roll that forward. Okay, so these are the annual returns over rolling 12 month periods. That's the 12-month return over this 12-month period right here, which is from February 1st of 1950 to January 2nd of 1951. So these are just rolling 12-month returns. And what I want to do is I want to test our inferences here. So let's just do an actual count. And what I mean by that is how many of my observations were below the lower bound and above the upper bound. Going to be very easy to execute. I'm just going to do count if, and I'm going to highlight this range. I'm going to lock that in. And what I want to know is how many of those are less than, and you got to put it in quotation marks, the lower bound. And you have to put an ampersand in front of that lower bound. Okay, easy enough. Should be able to drag that formula actually down. And now I want to do how many of them are above the upper bound. So count if, again, highlighting the range, locking it in, but now we're doing above. Again, you have to give it the ampersand, and so there's your formula. And dropping it down. We can center that. And again, let's just format it. Okay, so we have our count, 122 times. Actually, let's just focus right here. So as we suspected, okay, with negative skewness, we thought that we would see most of the outliers on the negative side, and we do. 10 times, the return dropped below this 99% lower bound of negative 36.89%. However, it never got above the upper bound. That's just manifesting the skewness. I actually want to check the percents though, so I want to calculate these as a percentage of however many 12-month rolling periods we have. So let's see this as an actual percent. I actually just want to kind of copy that actually. Except now we're not going to do a count, we're going to do a percent. So all I want to do is I want to take that and divide it by however many rolling 12-month periods we have. So I'm going to just lock that in. So there's my formula. It's just the number of times we go outside of our bound divided by the total 12-month rolling periods. We can drop and drag that all the way across and turn them into percentages because that's how we want to interpret it. Center it. Okay. And now we can make some very helpful inferences from this. Please notice, if this were a normal distribution, then 99% of the time we would have expected the annual return over any 12-month period to be between minus 36.89 and positive 51.08. We know there are fat tails. The kurtosis is above 0. So actually, instead of having 1% outside of that bound, we expected there to be more than 1% outside of that bound. If you add those together, you'll see that. What we can see is that instead of 1% being outside of the bound, we have 1.35%. And right here, instead of 5% being outside of our band, we have 5.68%. And here, instead of 32% being outside of the band, we have 33.38%. So indeed, we see the kurtosis, we see the fat tails. Probability of extreme observations is a little bit higher than a normal distribution. Also consistent with the negative skewness, we thought that most of these extreme observations would probably be on the negative side, the left tail. Focusing here, actually, you can see that all of the extreme observations are in the tail. This is somewhat bad news for investors. What this means is, on average, generally speaking, you can expect most of your annual returns in the S&P 500 to be between negative 36.89% and positive 51%. However, there's actually slightly more than a 1% chance that your annual return will fall outside of that band. And based on historical data going back to 1950, all of those extreme observations are going to be in the left-hand side, in the negative tail, which means you have slightly more than a 1% of you have slightly more than a 1% chance of losing more than 36.89%. And so I just want you to see how these summary statistics can be estimated and how they can actually be validated, and the caveats that you need to be aware of. So never, 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 never stop at mean and standard deviation. Always pay attention to skewness and kurtosis, and never, never, never stop at just your 68, 95, 99% band. You can get your clocks cleaned if you're not careful. And I can actually show you quite specifically. So let's scroll down and I can show you where these extreme outliers are. And you won't be surprised. Go back to 2008. And you can see that over these 12-month periods right there, we are outside of our 99% lower bound. And so how many is that? That's 8. You can see there were only 10 12-month rolling windows that were outside of that band. 8 of them occurred during the financial crisis of 2008. So I hope this helps to give some context to the summary statistics that we've been studying in class. And I hope it also gives you some useful tools that you can apply to assets and portfolios. Please keep in mind, just as one final piece of warning here, this is most applicable when the central limit theorem holds. And the central limit theorem holds when we have a higher number of observations. So what that means is this type of analysis is especially useful when we're talking about portfolios and lots of observations. So the more assets you have in your portfolio and the longer the time series, in other words, the more months or days that you're analyzing, the higher the probability that the central limit theorem is going to hold. If you're looking at a single asset over a narrow time period, there's a very low chance that the central limit theorem is going to hold. You won't have a normal distribution. And all of these 68, 95, 99% bounds are going to be very unreliable. Anyways, hope this was helpful. Hopefully you can complete the assignment. Again, you can always contact myself or the TA. Best of luck.